Okay, hello everyone. Good afternoon and welcome to this final workshop of the Crash&Tough project. First of all, let me introduce myself. I'm David Frometa. I'm Dr. David Frometa. I'm the work as a researcher in the unit of metallic and ceramic materials of EURECAD. I've been the project coordinator of this Crash&Tough project, and I will be also the moderator of the session today. So I hope you enjoy the presentations that will be show today during the event, and we all can learn a little bit more about this third generation advanced high-strength steels and its application to the automotive industry. Now, without further ado, let me start with the first part of the presentation. It's an introduction to the workshop and a short project overview. First, let me present the agenda for today. This event has been organized or has been divided into two different sessions. And the first one, we will provide this short introduction and project overview, also together an introduction to the third generation advanced high-strength steels, metallurgy, processing, and mechanical properties. Together also the advanced microstructural and mechanical characterization techniques for these steels. Then after the first session, a short break of 15 minutes. And then we'll be back with different presentations talking about crash resistance evaluation of advanced high-strength steels, advanced modeling approaches to improve the accuracy of crash simulations, and finally, the industrial implementation of this new third generation steel grades in automotive components. By the end of each session, we have reserved this time slot around 10 minutes for each session to answer your questions. So please, during the presentations, write your questions down in the chat, so we'll collect them and we'll try to answer to all of them during these Q&A sessions. Okay, well, now before continue with the presentation, I wanted to remind that this workshop, this webinar will be recorded. So at the end of the event, we'll share with all the participants both the video and also the presentation that we will show during the workshop. First, let me start saying some words about the project, some general information about the Crash&Tough. The Crash&Tough is an European project. It is funded by the Research Fund for Coal and Steel program by the European Commission. The full title of the project is Towards High Crashworthiness Parts through the investigation of microstructural effects and fracture toughness of third generation advanced high-strength steels. Of course, the acronym is, of course, Crash&Tough. The project had a duration of 42 months. It started on the 1st of July of 2018, and it recently finished the last 31st of December of 2021. Here you can see more general information, the agreement number and the participants. The project has been coordinated by EURECAD as a research center. It has also the participation of the Fiat Research Center, also the Luleå University of Technology, and the two steel makers, voestalpine and ArcelorMittal. Now some introductory words also about to understand the motivation and why to focus on third generation advanced high-strength steels. Well, as you probably know, these advanced high-strength steels are high-performance steels that are characterized with unique or complex multi-phase microstructures that provide them unique mechanical properties, combining high strength and good formability. The use of these kind of steels, of these high-performance steels, of advanced high-strength steels, has increased exponentially in the last years. As an example, you can see here, a current model of an automobile can have up to 56% of advanced high-strength steel in the body, in the console, on the body in white. So these steels are especially suitable for this crash or safety-related applications, and they have definitely contributed to improve the safety of the passengers while reducing the total vehicle mass. So, well, this is steels also. This family of sophisticated steels has been evolving also during the last years. from the first generation of advanced high-strength steels, including this dual phase. Normally you have heard a lot about that, dual phase, complex phase steels or martensitic steels. Then evolved to the second generation of these tube steels, which are characterized also by very high formability and high strength. But then now the focus of the research, the research is focused on this third generation of advanced high-strength steels, covering this gap or this jump between the first generation and the second. These steels are characterized by the showing also comparable or higher strength even than first generation steels, but also with improved formability, while they are also characterized by the reduced cost compared to the second generation of steels, which are also more expensive, also mainly because of the high alloying content. These steels also have a high lightweight potential, as I mentioned. Here is some data provided by Arcelor in this case, where they claim the replacement of the first generation dual phase steels by current generation of third generation triple-sided steel grades can suppose a weight reduction up to 10%. Then if we look into the future third generation triple-assisted steels, these weight savings can go up to 20%. So we see that there are important weight savings. Some similar information from other source. In this case, this is data provided by CRF, and then they share with us for the project. Also replacing this first generation dual phase steels by third generation triple-assisted steels in different components. They obtain this weight saving in different components. They obtain this weight savings from 14 to 19%, which again you see that are important savings, and while maintaining or even improving the safety performance of these components. Well, let's see what are the objectives of the project and also the main outcome. The main objective or the aim of this Crash&Tough is to develop high crash resistant steel solutions based on this third generation advanced high strength steels. How we do that? Mainly because through the investigation of the effect of microstructural constituents, crack initiation and propagation resistance, in order to optimize their microstructure for high fracture and high crash performance. The specific project objectives are listed as follows. The first one is to obtain a profound knowledge about the microstructural effects on the fracture resistance and crashworthiness. Second is to characterize the crash behavior of these different trip-assisted steel microstructures by means of a small-scale laboratory test, including V-bending tests according to VDA 238 and 100, also fracture toughness measurements, larger scale semi-industrial impact resistant tests based on axial and bending impact tests. Also, an important part of this project is the development of improved finite element models to better predict the crash behavior. So this includes the development of new damage models and new failure criteria based on these strain and energy-based damage models that will be implemented to improve this accuracy of these crash simulations. And finally, also to try to validate the implementation of these new steel grades in the industry, in high crashworthiness automotive parts. Regarding the results or the main outcome of the project has ended with a greater knowledge on the relation microstructure fracture resistance of third generation advanced high strength steels, together with these new finite element models for crash simulation I mentioned briefly before, and then we will see later in the next presentations. And we expect that these achievements also will contribute to foster also, first, on the one hand, the development of new third generation steels or chip-assisted steels microstructures, and also on the implementation of these kind of steels in high performance and safety related automotive components. Finally, briefly to talk about the project structure. The project has been structured in 7 different work packages. Then, each one of them was coordinated by one of the participants. Web package 1 was directed to the microstructural and mechanical characterization. Then in web package 2, we performed a series of small-scale tests to estimate the crashworthiness of the investigated steel grades, and namely the bending test and also fracture toughness measurements by means of the essential local fracture methodology. Then in web package 3, we perform a more semi-industrial laboratory axial and bending impact resistant test, also together with alternatives to dynamic tensile tests at different strain rates, so to characterize the dynamic response of these steel grades. Then in web package 4, we conducted a detailed microstructural investigation with means of different techniques like Ebsd and indentation, as also we will see later in further presentations, to better understand the role of the different microstructural constituents on of strip steels in fracture and crash resistance. In web package 5, we have been working with this new damage models to improve the accuracy of the simulations, on the development of these new damage models based on the strain and energy-based damage model that we will see more in detail later. And then all this converged in the web package 6, where we implemented the results in industrial automotive parts. Also the web package 7, which is related to the management and coordination, which was led by RECAD. And well, I think that's everything from my side. Thank you very much for your attention. And now I think we can move on to the first speaker of today. This is Johannes Rell, Dr. Johannes Rell. Johannes is a senior researcher at the materials development for cold rolled products and voestalpine. And he will talk about I'll give an introduction. The presentation is titled Third Generation Advanced High Strength Steels, Metallurgy, Processing, and Mechanical Properties. So please, Johannes, the floor is yours.
So I hope you can see the presentation. Can everyone hear me?
Yes, we can hear you.
Okay. Thank you very much. My name is Johannes Rell. I'm a senior researcher in the Department for Materials Development for cold rolled materials, and I'm working on the third generation of AHSS grades. Just a few words regarding the agenda. First of all, I would like to give a short overview about the first, second, and third generation AHSS. Then I will show you the steel grades investigated, the mechanical properties, the microstructure of the grades, and finally some words on the stability of the retained austenite of the steels. Well, in the project, we investigated 4 steels of the first generation and 4 grades of the third generation AHSS. This figure gives you an overview regarding the placement of the first, second, and third generation in the so-called steel banana. In the first generation, we have the trip steels with very high elongation values, followed by the dual phase grades. Then we have the complex phase grades in the first generation, which show the highest strength levels but lower elongation values. In the second generation AHSS, we have the trip steels, which show very high elongation values, and between the first and third and second generation, we have the third generation AHSS, where we have the dual phase high ductility grades, the complex phase high ductility grades, the DBF grades, the CFB, and the quench and partitioning grades. And in the Crash&Tough project, we investigated grades with strength from 800 megapascal to 1200 megapascal. Generally, we can say that the AHSS steels of the first generation show quite high strength and a balanced ductility. Typical phases in this multi-phase microstructure are soft phases like ferrite, bainite, but also harder phases, that means martensite, tempered martensite, and some retained austenite. And the grades in the third generation AHSS are multi-phase grades with an increase in global and local formability. That means these grades show high elongation values, well, good bending values, and they have an improved edge cracking behavior. The grades contain retained austenite in a binitic or martensitic matrix, including other phases, that means soft and harder phases in specific proportions and distributions to gain these enhanced properties. The steels have retained austenite, and this retained austenite enables a trip effect. That means we have a strain-induced transformation from austenite to martensite, and this enables an increase in uniform elongations due to an improved work hardening behavior. Here you can see a typical annealing cycle for trip-assisted binitic grades, the DBF grades, and for carbide-free Finite grades respectively. And one very important step during the annealing process is the overaging step. That means the isothermal binitic transformation step, where stabilization of austenite due to carbon redistribution is performed. Typical naming for this DBF grades, for these CFB grades, are dual phase high ductility grades, DBHD grades, and as I said, DBF for CFB grades. Then we have the quench and partitioning grades, the so-called QMB, the QB grades. Here again, you can see the typical annealing cycle for these grades. We have two very important steps. We have the quenching step, where a particular amount of martensite is generated to get the martensitic matrix for the material, and then we have the partitioning step, where again the stabilization of the austenite due to carbon redistribution from martensite to austenite is performed. Typical naming for this QNB grades is complex phase high ductility, or CPHD, or quench and partitioning, or QP grades. Well, to get this elevated local and global ductility for this third generation grades, a particular content of retained austenite and optimal stability of the retained austenite has to be achieved. So we have to say that alloying and annealing are well balanced for these grades. For alloying, for example, we use silicon, aluminum, chromium to avoid the cementite precipitation, so to have the carbon in solid solution to stabilize the retained austenite. Then we have carbon and manganese in the steels for chemical stabilization of the retained austenite. We use microalloying to get a particular morphology to stabilize the austenite. And during the annealing steps, we control the ferrite, the bainite, the martensite, and the content of retained austenite. We control the carbon redistribution. We regulate the mechanical stability of the retained austenite, and we generate a particular morphology and a good homogeneity of the retained austenite and the other phases in the microstructure. Well, especially for the optimized local ductility of this third generation grades, hardness contrasts in the microstructure have to be minimized, and a homogeneous distribution of hard phases is necessary. This table gives you an overview of the steel grades investigated in the project. So we had three strength classes. We had a class with 800, class with 1000, and a class with 1200 megapascal. In the class with 800 megapascal, we had two trip steels, and we had one DBF CFB grade. In the 1000 megapascal class, we had two dual phase grades. And in the class with 1200 megapascal, we had two DBF CFB grades and one typical Q&B grade. The grades had different thicknesses, so please keep in mind that different thicknesses may have an impact on stiffness, on essential work of fracture, on bending strains, and energy absorption for crash tests. This table shows you the mechanical properties of the steel grades investigated. So the two drip steels in the class of 800 megapascal had the highest content of retained austenite and showed the highest elongation values. The dual phase high ductility grade in the strength class 800 megapascal had a lower yield ratio, a lower yield strength when compared to the drip steels. In the 1000 megapascal class, we had one dual phase grade with about 6% of retained austenite and one grade with neglectable content of retained austenite. And in the class 1200 megapascal, we had one DBF grade with low yield ratio, with lower yield strength, one DBF grade with higher yield ratio, with high yield strength. Both DBF grades had the same content of retained austenite. And as I said, we had one QMP grade, and this QMP grade showed the highest yield ratio, the highest yield strength, and also quite high total elongations. Here you can see SEM images of the grades with 800 megapascal. I would like to give you some information about the microstructure for the grades investigated. Well, the DFB grade, the DP800 high ductility, had a matrix of ferrite and bainite with some martensite retained austenite islands. When compared to the drip steels, this dual phase high ductility grade had an increased content of martensite and lower retained austenite content. And both drip steels had a matrix of ferrite and bainite with martensite retained austenite islands and very high content of retained austenite. On the left-hand side, you can see the dual phase grade, strength 1000 megapascal, which had some retained austenite. This is a more complex microstructure with ferrite bainitic matrix, some tempered martensite, and finally distributed hard martensite islands and some retained austenite. And on the right-hand side, you can see the DP1000 grade with neglectable content of retained austenite. This grade has ferritic bainitic matrix with distributions of martensite islands. And here you can see the SEM images for the grades with 1200 megapascal strength. On the left-hand side, you can see the DBF grade with low yield ratio, with lower yield strength. This grade has a bainitic matrix with globular and lamellar islands of martensite and retained austenite and some tempered martensite. Is also obvious for this grade. In the middle, you can see the DBF grade with higher yield strength, with higher yield ratio. This grade has a bainitic matrix with retained austenite leads and more globular martensitic retained austenite islands. And on the right-hand side, you can see the QMP grade with high yield strength and high yield ratio. This grade consists of a matrix of tempered martensite with retained austenite leads and some bainite. Finally, some words on the stability of the retained austenite. We investigated the stability of the retained austenite, and therefore we measured the decrease of retained austenite depending on the plastic deformation of the material. That means the lower the decline of retained austenite content with increasing plastic deformation, the higher is the stability of the retained austenite. And you can see that we had a very high stability for the retained austenite for both drip steels and for the higher, for the DBF grade in the class 1200 megapascal with higher yield strength, as well as for the QMP grade. Then we had a high stability of the retained austenite for the DBF grade in the 800 megapascal class, and for the DBF grade with low yield strength in the class 1200 megapascal. We had a quite low stability of retained austenite for the DB grade in the class 1000 megapascal, which had about 6% retained austenite, and we had a very low stability of the retained austenite for the TP grade in the class 1000 megapascal, which had hardly any content of retained austenite. So the grades had different content of retained austenite as well as different stability of the retained austenite. Finally, I would like to summarize the most important information about the steel grades. Well, as I said, we had 3 strength classes. In the strength class 800 megapascal, we had 1 DP800 high ductility, that means a DBF grade. This is a typical DB grade with a low yield ratio and enhanced ductility due to a trip effect from the retained austenite. Then we had 2 trip steels with very high content of retained austenite and very stable retained austenite and massive trip effect. In the strength class 1000 megapascal, we had 2 DP grades, 1 grade with a more complex microstructure and some retained austenite, and the other grade has a microstructure consisting of ferritic granitic matrix with martensite islands. This grade had a neglectable content of retained austenite. And then we had the class with 1200 megapascal, where we had 2 DBF grades with different yield ratio. These grades had a binitic matrix with retained austenite in multiple morphology. And we had 1 QMP grade with very high yield ratio with a matrix of tempered martensite and some retained austenite. And all the grades in the class of 1200 megapascal had a trip effect, which enabled the enhanced ductility. Well, thank you for listening, and let's move on to the next presenters.
Thanks a lot, Johannes, for the presentation. Sorry for the technical problems, but okay, that's our live show problems. Don't worry. Now, well, we can continue with the presentations. Now it's my turn again. I will talk about the fracture toughness evaluation of advanced high-strength steel sheets. Let me share my presentation. Okay. Hope everyone is seeing the presentation correctly in the presentation mode.
Yes.
Okay. Okay. Thank you, Marina. Then, well, the objective of this presentation is to talk a little bit about why we consider that it's important to measure the fracture toughness in these thin advanced high-strength steel sheets. Well, first, let's start by the introduction. Well, I will not waste more time in this. I will not spend more time in this part of the introduction. We have mentioned also in the beginning, in the first presentation, in the second, all the advantages of these advanced high-strength steels and how they have contributed to increase the safety and to lower the total weight of the vehicles. But now, well, not all are advantages with this kind of steels, but they also have brought new challenges related, especially to these high-strength materials, related to the moderate ductility and higher cracking susceptibility, for example. Some real-life examples is, for example, the occurrence of edge cracking during cold forming, which is more and more recurrent with the use of advanced high-strength steels. So as we move to steels with higher and higher strength, it's probably some more frequent. Also, other kind of problems related to this crack formation is the crack formation under impact loading. For example, we can see here samples we have been crash tested, and we can see some of them show this degree of necking. Well, as I mentioned, these fractures are more and more frequent with this kind of advanced high-strength steels. So it is evident that we need new fracture or also new fracture criteria, and concepts like the fracture toughness or damage tolerance of these steels should be considered. Because unfortunately, the conventional tensile properties cannot define this kind of cracking behavior for this kind of steels. So that's why in advanced high-strength steels we should differentiate between the global and local formability. The global formability is the one, the traditional definition of formability, which is the resistance against the necking instability, and is well represented by conventional usual forming operation with deep drawing, and is well represented also by forming limit curves or conventional tensile parameters based on the elongation through uniform strain, for example, or the strain hardening exponent. Then, on the other hand, we have the local formability, which is more related to the fracture resistance of the material. Some examples of local formability operation modes are this edge formability, or the bending on tip radius, or the crash folding behavior. For representing the local formability of advanced high-strength steels, different parameters have been proposed in the last year, like, for example, the hole expansion ratio, which is well known and well established for edge cracking resistance measurement. So the true fracture strain from the uniaxial tensile tensile test measured from a reduction of area from the fracture surface of uniaxial tensile specimens, or the set value, or the bending angle from the bending test according to the BDA. Also based on in these new parameters, even a new and advanced classification maps for advanced high-strength steel have been proposed, like this Hans diagram, where the true uniform strain is represented as a measure of the global formability, while local formability is represented by this true fracture strain. Okay, now besides all these approaches, what we think in this case, so if you are talking about problems related to the crack initiation and propagation resistance of the material, we think that we should consider or take a look into the property that controls this crack initiation and propagation resistance, which is the fracture toughness. Now let's see how to measure this fracture toughness in thin ductile sheets. One of the methodologies that we have seen, we have worked with in the last years is the essential work of fracture. We have seen that this is one of the most suitable methodologies to evaluate the fracture resistance or the crack propagation resistance of thin metallic sheets, not only of advanced high-strength steels, but also high-strength aluminum alloys and all kind of ductile sheets. The method is very simple compared to other fracture mechanics standard procedures, and it allows to separate in an easy way the energy developed for so the specific energy for fracture from the also the energy related to the plastic work in fracture. Okay. The method is quite simple. You only have to test. In this case, you can use any kind of fracture mechanics test the specimen, but in this case we use Dent Test specimens or double-edged notch tension specimens because are more simple and also they facilitate the test. And you need then the specimens with different ligament lengths, which is the distance between the two cracks, and you test them up to fracture and calculate the fracture energies. So by means of simple mathematical and statistical analysis, you obtain this specific essential work of fracture, which represents the crack propagation resistance of the material, and it could be somehow in certain materials could be related to the elastic plastic fracture mechanics value, the JC. Okay, but one of the good points of this method also allows to separate in a very easy way between the crack initiation resistance, or the energy for crack initiation, and the energy for the full propagation, which is the essential work of fracture. I said this is a very simple method, which is extensively used for characterizing the tearing resistance of ductile polymer films. There's no need to crack monitoring, so you have to measure the crack during the test, which is one of the greatest talent in this fracture mechanics test. And as we will see now in the next slide, it has become of great industrial interest, because we have shown in the last year that it's very useful to understand the overall fracture performance of high-strength metal sheets and problems like edge cracking or the cracking under impact loading. Now let's see how to apply these essential work fracture measurements to understand the fracture performance of advanced high-strength steels. First, take a look to the edge cracking resistance. We know that this edge cracking resistance is usually measured or is quantified by means of this hole expansion test and the hole expansion ratio, which is a measure of this stretch flangeability of the steels. It is well established. It's a simple method, but the reliability of these tests are often put into question, because there a large variability. There is not a material property, and it depends on many variables, like the punch to die clearance, also the alignment of the tool, the operator, the system that they use for crack initiation and detection, and so on. So that's why researchers have been working a lot, dedicating several efforts to find mechanical properties that can somehow define in a more objective way this stretch flangeability. That's what we have done with essential Walker fracture, and here you can see a comparison or the correlation between this Hall expansion ratio and the essential Walker fracture for a wide range of advanced high-strength steels, including also first and third generation steel grades of different strength classes, from 800 to 1500, where we can see the linear correlation, the good relationship between this fracture toughness measured through the essential Walker fracture and the Hall expansion ratio. So tougher materials, and say materials with higher crack propagation resistance, also show higher edge cracking resistance. Something similar occurred with when we look at the crash behavior in a previous project. Okay, well, also the crash behavior of in axial impact test, also for several advanced high strength steels, was measured or was quantified using a cracking index and also the energy absorbed at maximum intrusion. When we observed that these steels with higher fracture toughness in general showed better crash behavior. What we observed from the test is that the materials with low fracture toughness showed rapid crack propagation, poor crash foldability, and overall lower crash performance. On the other hand, steels with high fracture toughness show small crack propagation, high crash foldability, and a higher crash performance. Okay, so based on this and seeing that this fracture toughness can give important information about the fracture behavior of the material, what we propose in one of our latest papers, which was also developed during the execution of this project, is to propose also new classification maps, also accounting not only with the global formability, but also with the cracking resistance measured by the specific essential Walker fracture. Also, alternatively to the traditional banana plot, when the total elongation is plotted against the ultimate tensile strength, well, we propose as alternative also to consider this specific essential Walker fracture to better classify, to have a better or more comprehensive description of the overall fracture and fracture performance. Okay, now let's see some of the essential Walker fracture results we obtained for the materials investigated in this project. Here, also the materials that Johannes presented in the previous presentation. Here are grouped by the strength class. We have here the results for the 780 megapascals, here for the 980, and here for the 1180 megapascals steels. Well, one of the first things that we can see here are represented the values of a specific essential Walker fracture, which are the gray values, the gray bars, I'm sorry, and on the other hand, the crack initiation resistance values, okay, in blue. The first thing that we can see is, well, while some materials show a small contribution from the total crack propagation resistance after the initiation, because, well, you can see that the initiation and the full energy for propagation is quite similar. But we can see in other, like the DP 900 AM or the TRIP 780 from voestalpine, that this contribution after the crack initiation, this energetic contribution to crack propagation resistance is very high. So a single parameter for crack initiation is not sufficient to define the overall fracture performance. Another important message here is that, well, we wanted to repeat is that this crack propagation properties, crack propagation resistance, cannot be estimated from tensile properties. Here we plot the specific essential Walker fracture for all the steels investigated, also as a function of different tensile parameters, the strength, the ultimate tensile strength, string hardening, uniform elongation, total elongation, also the product of the UTS by the total elongation, which is usually also used as a toughness indicator. But we can see here that there is no correlation between the crack propagation resistance and any of these parameters. Also, the traditional way of thinking, the materials with higher elongation or with higher string hardening are supposed to be with greater fracture or to show greater fracture toughness. This is not true. We can see that in advanced high-strength steels, also rather on the contrary, often this trend is the opposite. No? So steels with higher elongation can show lower crack propagation resistance. So the important here is to highlight the fracture toughness cannot be estimated from tensile properties, and it should be properly measured in the frame of fracture mechanics. Here also as an exercise, we wanted to put all the values of the central wall fracture in the classification map that I showed in the previous slide. And we can see more or less where they fit, this 780 degrees, the DP and TRIP, more or less in the same group of similar steel grades. Regarding the DP 980, you can see also the DP 980 from Stelpin, more or less with similar values to other steels of dual phase steels with similar strength level. In this case, also we could observe this very high fracture toughness for the DP 900 from Arcelor, which also is more closer to other complex phase steels. And finally, this regarding the 1180 degrees, we can see, for example, the QP is also in the group of Q and P steel, so it shows it's in a good agreement with other Q and P steels. It's investigated in other projects, as well as this DP 1180 and HF 1180 CFB, which are also in the according to the classification proposed. Finally, to say some words, now we have seen the importance of measuring fracture toughness and why it is important, and it will be more and more relevant as we develop new steel grades with improved properties and with complex multi-phase microstructures. Now I wanted to show or to explain some of the measures that we are trying to foster the industrial implementation of this fracture toughness measurement. On the one hand, the first is regarding the standardization, because there's no standard method yet for this essential wall fracture methodology. There's a testing protocol developed by the European Structural Integrity Society, which is intended for the fracture characterization of polymers. In this sense, in another European project, which is called Formplanet, we developed this FEN workshop agreement, which is called the test method for determination of the essential wall fracture of thin ductile metallic sheets. It was developed by EURECAT, also in collaboration of other standardization institutions like UNE and DIN, and also, of course, of the other players relevant in the sheet metal, like the ArcelorMittal, Sogetamec, and Frickroll. If you want to, you can check the document and access in this link. Okay, after the meeting, also we'll share this presentation, so you can also have access to this new testing protocol. Also regarding also other related projects and related to this fracture toughness, there's an ongoing RFCS project, which is called Tough Steel, fracture toughness as a tool to address cracking problems in forming and incentive performance of advanced high-strength steels. It's a valorization and dissemination project. So this is intended to spread the word about all the work we have been doing during these years in previous projects to the industry, to show the benefits of these fracture toughness measurements and how it can be helped to solve these problems related to the cracking resistance. Also the project has a duration of 2 years, and it has the participation of 8 partners from 4 different European countries. Also, it's coordinated by EURECAT. And well, I will inform you in the chat. We'll put then some information about next events and more information about them. Thank you very much for your attention. I stop my presentation, and now I think I leave the floor to Matteo Salib, Dr. Matteo, which is a research engineer at the Research Product Center at ArcelorMittal Global R&D, and will present the advanced microstructural characterization by means of Ebsd. Please, Matteo.
Thank you, David. I share my screen and my camera. Can you see me?
Yeah, I can see it.
Yes. Okay. So I put it in full screen. So as said, David,
you can see your jacket. If you can put in front of the camera, or...
This is a second screen, so I'm far from. Okay. Okay, so I'm Mathieu Salib. I'm working in ArcelorMittal as an engineer, and I'm specialized on the characterization of microstructure, of steels, and especially of Ebsd. So the objective of this presentation is to show you the influence of fracture on microstructure. So this is the plan of the presentation. So first the objectives, then I will just show one slide on the Ebsd technique and the different parameters that we have highlighted to see the evolution of the microstructure. Then the main results on the evolution of the microstructure with the deformations and some conclusions. So the objective was mainly to determine the influence of crack propagation on a microstructure. So to do that, we focused on Dent tests. So some interrupted tests in order to have the evolution of the fracture of the crack all along the microstructure at different states, which we called 0, 1, 2, and 3. The 0, 1 is the pre-crack. The first state, the crack is not yet has not yet moved. Then in the state 2, we initiate the real crack here. And in the stage 3, the crack is propagating. And we have observed this evolution on the 5 grades. So the 2 DP980, the 2 HF1180, and the DP1180 HD. So the technique of Ebsd. So why using Ebsd? So first, to observe and quantify the microstructure. So we are able to detect the type of microstructure, and we can finally quantify the fresh martensite. We can also quantify the grain size in average and in distribution. And for martensite microstructure, we can identify the micro constituent size and location of the crack through the interfaces of the martensite. And secondly, we can observe the evolution of the deformation induced by the crack. So we can localize the deformation zone in direct link with the crack propagation. We can quantify the density of GND, some dislocations. And we can also see the evolution of the constitutive phases only if the size is enough for the characterization by Ebsd. And I say that below 300 nanometers, it's beginning to be difficult to quantify clearly the phasing presence. So a slide to show the different representation of maps that we have used. So first, phase maps for the different constituents. So for instance, the BCC phases or the FCC, the audiostenites. The IPF maps on which we can see the orientation of each pixels. And it's interesting because we can see the different grains and grain boundaries. This is the main maps that we can have in the literature. This is what I think you are used to. And two other maps, the GOS one, which means grain orientation spread. So this is an example. And we can see with the GOS the average misorientation inside one grain. So one color equal one grain. And so we made the hypothesis that the misorientation is due to a rotation of the crystalline lattice. And so this is due to a local deformation. So through the Gauss, we are able to see if the grain is deformed or if it is recrystallized. And for example, this is a microstructure fully recrystallized, and this is a microstructure deformed with some elongated grains. And finally, the CAM maps, which means a kernel average misorientation. And here we look at the local misorientation at the pixel size, and the same hypothesis or locally, if we have some misorientation, we can say that we have some local deformation. And so here we have one color equal one pixel. And through the CAM maps, we are able also to quantify the GND, the geometrically necessary dislocations, through this formulae, which consists of the step size, a constant, the CAM value, and the Burger's vector. Okay, so the main results. So the evolution of the retained austenite. So at each step, I only show the maps which come from the HF1180 CFB. And after, I will show you the quantify the value. So what we can see at the receive state, so the state the 0, we can see some austenites, but after the crack propagation, there is no austenite anymore, and this is what is represented on this graph with the orange value are the Ebsd far from the crack, and the gray one the austenite close to the crack. And so we see that close to the crack, whatever the sample, we have no austenite anymore. And we can also see that the difference between Ebsd and XRD, in which we see that Ebsd is not the technique the most suitable to characterize the austenite, because this is too thin. And so what we say here is that the deformation induced by the crack has transformed the austenite into the Martensite by trip effects. We can say that by the comparison. Here we see through the IPF maps the evolution of the grain size, of the mean grain size as a function of the deformation. And so this is the receive state, and this is the state 3 close to the crack. And what we can see is that we have close to the crack a lot of new grains with high angle grain boundaries which are formed. And so we have a formation of a substructure with dislocation cells of an average of 0.4 micrometers. And this formation of the substructure is observed in the 5 materials. So here we have the average grain size as a function of the product for the 4 states. And what we can see is that in average, when the crack propagates, the average size decrease with, and this is due to the presence of the substructure. Yes, and at the stage 3, the average effective grain size decreased drastically of 2 times. So this is a real evolution. And we have seen in the literature that this kind of substructure was already observed by TEM, and that the dislocation cells was around 0.5 the micrometers, close to what we have seen. Now with the Gauss maps, we can see the evolution of the deformation. And what is again the HF 1180 CFB, and this is far from the crack and close to the crack at the state 3, or we can say the state 0 and the state 3. What we can see when we zoom on the state 3 is that the presence of this substructure, and that these dislocation cells are dislocation free, and that they are separated by high angle grain boundary. But inside the cells, there are no dislocation, no misorientation. And this is also observed in the 5 materials. And I represent here the evolution of the GOS. So on the state 0 and 1, almost no deformation is induced. So there is no difference in terms of GOS. And at the state 2, the GOS value is increased for the 5 materials. It means that even if the crack is only at the initiation state, there is an evolution of the deformation in the grains, and this evolve also at the state 3. And also we have seen in the literature, so the formation of the substructure, which are composed of dense wall or grain boundaries. And so this is we can compare that to the formation of new high angle grain boundaries, and this is what we can see on this GOS map here. And finally, the evolution of the deformation at the local in local, yes. So we can see through the CAM maps that between the zone far from the crack and close to the crack, that all the surface analyzed by Ebsd here is impacted by the deformation, and that we can see that close to the crack there is also more deformation. And so we can say that all the phases are impacted by the deformation. So this is a fact. And in the stage 3, the global CAM value is higher, linked with the deformation. It seems that locally, close to the crack, the deformation, yes, is no higher than far from the crack. So we can see that here and here there is no difference in terms of CAM, so no real difference in terms of a deformation.
Sorry, Mathieu, we are
yes,
a little out of time.
Yes, this is the end, but it's only 14 minutes. 14,
Okay.
yes. And just to finish, so in average, we can see that, so we calculated some GND density, and it evolves with the deformation, and we can have some quantified value of GND. So this can be some input for models. Yes, and we can say that at the stage 3, we have double the number of dislocations. So this is all. And yes, just to say that we have the same results at the surface and at mid thickness. So we can say that all the observations that we have made on the surface are the same in the whole volume. Okay, this is all, and the conclusion is only what I was saying. So I think I have nothing to add. Okay, thank you.
Thanks a lot, Mathieu. Sorry for interrupting. I also well, we are 5 minutes behind the schedule also. Well,
Yes.
so my fault.
Okay.
Okay, maybe we can recover some minutes after in the Q&A session. Then we can move and give the floor to the next speaker, is Dr. Nuria Cuadrado. This is researcher also at the Metallic and Ceramic Materials Unit of CAD. And she will present the micromechanical evaluation through nano indentation. So please, Nuria, when you're ready.
Thank you, David, for your introduction. So I'm going to present. Okay, today I'm going to present briefly the influence of the microstructures of these third generation steel grades on micromechanical behavior and in the fracture toughness of these steels. Briefly, I will talk about the objectives, the nano indentation technique, the effect of the microstructure over the crack path and on fracture toughness, and then finally the conclusions of this study. The main objective of this study is to understand the role of each microstructural constituent on fracture toughness. Each microstructural constituent will have an effect on crack nucleation and propagation resistance. And we relate this crack nucleation and propagation resistance with the macromechanical evolution of the propagation. We use the specimens of essential work of fracture that in where fracture toughness is being evaluated. And in the same way as in Ebsd, we have done the micromechanical evaluation on stage 2, that is the initiation of propagation, and in stage 3, that it's before fracture, and in where crack is propagated. So, nano indentation technique, here we have a video. It's an instrumented technique that continuously control and monitor the loads and displacements of an indenter as it is driving into a material. We can obtain the curve, the PhD load and displacement curve, and with that curve and mechanical contact, we can compute hardness and elastic modulus mostly. We have done an array of 42 per 42 indentations. So we have a matrix done in the steels and covering an area about 200 microns. And we can obtain with this next technique a mapping of hardness. So we can see the distribution of hardness and this can be related with the microstructure. So move on and talk about the effect of the steel microstructure in the crack path and in the fracture toughness. So in this study, we are going to compare first generation steel grade, that is this dual phase 980, that doesn't have retained austenite, and we are going to compare this microstructure and their fracture behavior with the third generation steel grades. Very briefly, because microstructure has been explained before. DP, this dual phase, consists basically in ferrite, sorry, and bainite and global martensite. And it's important to note the lack of retained austenite in this grade steel. Here we can observe the crack evolution at the initiation of propagation and when the crack is propagated. And below these images, we can find the hardness mappings. We can observe how the hardness distribution evolves during the test. So we can observe basically that hardness is increased. In DP1180, basically, the initial state, the microstructure consists basically of a binetic matrix with blocky martensite islands, and the ruthenium austenite is present in this microstructure, show both needle-like and globular morphology. I want to point out the morphology of ruthenium austenite because it is important in order to understand the fracture behavior of these third generation steel grades. Below the images, we can find the hardness distribution, and we can observe that even in the initiation of propagation and when the crack is propagated, we can find in the mappings, in the hardness mappings, some small harder islands in both cases that we think that it's related with the drift effect. It means these little harder islands are the transformation of the ruthenium austenite to fresh martensite. We can observe that these little islands increases in the stage 3, where the crack is propagated. In the CFB grade steel, the microstructure basically consists of a binetic matrix with martensite islands, and I want to point out the arrangement of the binite lads. That you can see that these lads are linear and elongated. So this leads to a needle-like morphology of the ruthenium austenite. This is important because if you can see in this last image in where the crack is propagated, crack follows these lads of binite and follows also the needle-like morphology of the ruthenium austenite. So the crack is along the binetic grain. Here we can observe in the mappings of hardness that hardness increases a lot if we compare with the other materials. And again, we can observe these little harder islands that are related with the trip effect of the steel. Finally, here we can observe the QP that consists basically of a temperate martensite. In that case, the pronounced needle-like morphology of ruthenium austenite islands is a clear difference with the other steel grades studied in this project. Here, again, we can observe how hardness is evolving with the deformation during the propagation and initiation of the crack. And also, we can find little harder islands related with the trip effect. So, how these mappings and microstructure effects on fracture toughness directly from the mappings. Hardness mappings, we can extract an histogram and analyze in an approximate manner the hardness of each microstructural constituent present on the microstructure. Here we have all four steels, and we can observe that if we decrease the hardness difference between the phases, the crack formation is delayed. If we compare the fracture toughness at crack initiation, these results are from essential work of fracture. We can observe if the hardness of the microstructural constituent is smaller, this fracture toughness increases. So the best results are for DP, the first generation grade steel dual phase, and from the QP, because the difference between the microconstituents is smaller. This is because decreasing the hardness differences facilitates enhanced local formability. If we study the crack propagation for first generation grade steel, the dual phase 980, we can observe that crack propagates along the soft ferrite phase, linking the hard martensite islands. So it's like a network that all the hard, these small phases, these isolated martensite islands are connected through the propagation of the crack along the soft ferrite phase. If we study the crack propagation on third generation steel grades, we can separate the steels in two blocks. On one hand, we have the dual phase 1180 in the same way of the previous dual phase. Crack propagation is along the magnetic matrix, following and connecting the martensite island present on the microstructure. On the other hand, we have the CFB and QP steels that have little difference related with the crack propagation. In CFB, we can observe that crack propagates along the arrangement of the binitelites. And in the case of QP, crack propagates along the grind boundaries through the interfaces between firm or blocky rutile austenite and the temperate martensite matrix. It is important to note that in these both steel grades, CFB and QP, when needle-like rutile austenite films are perpendicular, you can see at the final of the crack propagation, when these needle-like rutile austenite are perpendicular to the crack propagation direction, they act as a barrier, difficulting the crack advance. So it's important to know. It's important to notice the difference between propagation and if we have needle-like rutile austenite or blocky or globular, more globular rutile austenite as in DP. Finally, if we check the properties, we can see that trip effect improves global ductility. This is the main results of the project. So trip effect improves global ductility, but may have a detrimental effect on fracture toughness if we can see the values of fracture toughness. But an optimum balance between global ductility and crack propagation resistance can be achieved through microstructural tailoring. It means that we can design the microstructure of the steel, taking into account the microstructural effects, and we can, in this manner, we can increase and we can improve the fracture toughness of the material. So to conclude, the main conclusions are the nanoindentation techniques. It's an easy and fast way to evaluate the effect of the microstructural constituents on crack initiation and propagation. Crack propagation resistance can be improved through microstructural tailoring, and initiation of propagation, the main conclusion is that decreasing the hardness differences between phases delays the crack formation because local formability is improved. About crack propagation, Crack propagates easily in a soft matrix following martensite islands, connecting these martensite islands. Neither like routine austenite films, difficult crack propagation when are perpendicular to the crack propagation, and harder matrix promotes crack propagation along grain boundaries, hindering crack propagation and increasing fracture toughness. So that's all. I've been fast, maybe.
Thank you, Maria, for the interesting presentation as well. Well, now we have some time for your question. I haven't seen too much questions, so I have one from the beginning of the session. It was made by Bundan Kumar Singh. Maybe it's directed to the first presentation, to the first speaker, to Johannes. Is trip effect taking place during stamping? Is it rate sensitive since it's better be used during crash rather than forming?
Well, of course, the drip effect takes place during the forming, and it also depends on the strain rate. Yes.
Okay. Well, also during the project we have seen, of course, that this drip effect depends on the forming steps, also on the strain, on the deformation path. Also we investigated how this transformation of retarded austenite to martensite evolves.
I would say it depends on the stress and strain state, and especially also on the strain rate.
Okay, thank you. I don't know if that answers your question. Also, I cannot see more questions, so I don't know if that everything is clear. Maybe you need more time after to digest all the information, and maybe you have more questions or more doubts or comments. Of course, you can arrive to us. Okay, then. Well, we have. I said I recovered the time because we were 5 minutes behind the schedule, but now more or less we are in time. We can do now a short break and come back in 15 minutes, okay, with more interesting presentations about this crash resistance evaluation, also advanced modeling approaches and the industrial implementation of these new third generation steel grades. Okay, see you at 3:40. Bye. Okay, welcome back. Thank you. I hope there. Now, welcome to this second part of the session. Now, the turn of Pascal Dietz. Pascal is a research engineer at the Microstructure Product Center at ArcelorMittal Global R&D, and he will present a presentation about crash resistant evaluation of advanced high strength steels. So please, Pascal.
Yeah. Do you hear me well?
Yeah, perfect. Thank you.
Okay, fine. So I share now my presentation. Okay, thank you, David. So in this part, we are having a look on the fracture strain results and some crash test results that were carried out in the lab of Mesial MS on the product we characterized in the frame of this project. So after a brief introduction, we will have a deeper look on the V-bending test and how we use it in order to determine the fracture strain in plane strain conditions. Then we will have a look on the sweep-on bending tests that were carried out on the HATSHAPE profiles. And finally, why we had to modify the test setup and the result we obtained on a modified profile, a notched sample in order to reach some fracture on this material. So if we have a look on the fracture criterion, generally it is given for a given strain path or triaxiality, depending also on another parameter here, for example, the load angle, and then it's a criteria that will depend on at least two parameters that will provide a fracture surface instead of just a fracture curve. But when we are using shell elements, it is plane stress condition, then we can have a formulation based on a fracture strain curve. And we can see that the lowest value of ductility is reached in plane strain condition. Here on the right graph for a structurality about 0.68. So that's why the plane strain condition is very relevant in order to characterize the product in terms of their ductilities. On the left side of the slide, we can see some crushed samples. Here we have only lab samples, but they are very representative of what happens on, for example, in this case, an axial crush of a front rail or rear rail, or even a crush box. And here we have a bending test performed on a sample, which is representative of a bumper beam or, for example, a B-pillar. And we can see that in the highly strained areas, the metal is actually folded. And then we can have a first evaluation of the behavior of the metal during a crash test by having a look on its foldability and how it will behave. And then we can consider some bending tests. Here we are considering the VDI 23800 standard, which defines such a test. We assume that the failure of the material will initiate after a stop criteria on the force is reached. It can be between 30 Newton loss or 100. Generally, we use intermediate values. Here we have the determination of the diameters, 30 millimeter, and the gap between the rolls, 0.5 millimeter plus 2 times the thickness. So the end must be below the graph, sorry. And considering this test, we can measure the displacement at failure of the punch, which can give an important result in terms of classification of the product. We can also measure the angle, which is generally considered by the car maker to evaluate the product. So how do we extract the fracture strain thanks to this result? So on the left side, first we perform the experimental test. We will measure the force versus the displacement, and we will take the displacement at failure, which is detected by the load drop. So here we take the value just before the load drop, the maximal force, and we will inject this displacement into a finite element simulation, which will take into account a fine plasticity description of the material, the correct setup, the correct thickness, so the same the correct gap, and we will virtually measure the fracture strain on the sample, which is actually the strain reached when the displacement at failure is reached experimentally, and then we can have the fracture strain. So this approach was applied on the 6 steel grades, the TRIP 800 from voestalpine, DP 1000 from both steel makers, and 1100 grades from also the both steel makers. And we will have some comparison of these results. But first, it's also interesting to have some validation of this approach. So this was done a couple of years ago in ArcelorMittal. We can see in this case that provided we are considering the same mesh size in the simulation, the blue curves, and the same grid size, the red curve, for DIC measurement, the simulation is in good agreement with the experimental test. Thus, it's possible for us to replace this purely experimental measurement by this hybrid approach first the test and then take the output of the test, the displacement type failure, as input for the numerical simulation, and then we will reach the fracture strain for all the product. That's it. So here what we can see is that first, all products have a big anisotropy of fracture. Generally, the fracture strain is always higher in rolling direction. We can also see that the best ductility is reached for the TRIP 800 product. Secondly, we can see that the Boost DP1000 grades have the same ductility. It's more or less equivalent for both in both directions. And finally, regarding the HF grades, they have very satisfying ductility and a little bit higher than the DP-HD grade. So that's for the classification of the product in terms of local ductility. Thus, in order to have a more realistic behavior evaluation of this product, we crashed some hat profiles. So the material is simply folded. You can see here's the section. It's a classical hat section, which is just bent. And we will then crash test this sample with a Ductile in Mézières. In given conditions, I do not go into detail. We just reach the same crush for all the sample, about 120 millimeter, which is a quite severe loading. It will induce a high plasticity of the hinge. And unfortunately, or by chance, or fortunately, it depends on the way you want to look the result. No failure was observed on any materials. It means this test was not severe enough. Here we have the results. So we can have here the general view of the crushed sample, and here locally, when we look at the produced bended area, there is no failure. So unfortunately, this test is not able to differentiate the product in terms of ductility, and it is not a severe enough test to hope a validation of the failure criteria that are developed by the partners of this project. However, we can measure the force versus displacement curve, and all these data were transmitted. They were shared with the partners, and they were able to validate at least the behavior of the material, even if it was not possible to validate some fracture criteria. That's why we wanted to modify the sample. We just machined a notch, we can see here on the drawings, in order to make a weak point on the section and to reach some failure. And in these very severe conditions, all the samples failed. We can see here that actually the displacement is in high excess, and the sample should have failed quite early. We can see that on the next slide, because during this test, we also measure the force versus displacement curves, and we can assume that when the force reaches the level of 0, the sample is completely broken. Unfortunately, it's very difficult to have an analysis of this test in terms of fracture initiation, because of the quite oscillating and noisy aspect of the curve. We are not able to correlate any force decrease with some initiation of the failure. But this curve were also shared with the partners, and they were able to make some correlation with the failure criterion in order to validate them. And that's all. Thank you very much.
Thank you very much, Pascal. Very nice presentation.
Thank you.
Now we can move to the next one. The next speakers will be Dr. Jorgen Kakaver. He's an associate professor at the Department of Engineering Science and Mathematics at the Lula University of Technology, and also Ricardo Hernandez, which is a researcher at the industrial area of EURECAD. And they will talk about advanced modeling approaches to improve the accuracy of crash simulations. So please, go ahead.
So I hope you can hear me and see the presentation as well. Would you please confirm?
Yes.
Yes.
Thank you very much. This will be a joint presentation between me, Jorgen, and Ricardo Hernandez from EURECAD. And it will be about modeling approaches to improve the accuracy of crash simulations. And what we have been seen so far during all the presentation is that the third generation advanced high-strength steels has an attractive combination of high strength, ductility, and good formability. And it makes this kind of steel a good candidate for car safety parts. But it has also been shown that in case a crack occurs, the crack propagation contributes significantly to the energy absorption. So this is a motivation to, in some way or another, introduce the concept of fracture toughness in the models. So if we go through the agenda or the outline of this presentation, we will start to talk about calibration of material models, and we will also highlight the importance of having mechanical testing at the deformation rates present in crash scenarios. And we will also calibrate a rate-dependent flow stress model, in this case the well-known Johnson-Cook. And we also have used a damage model, Gizmo. It is implemented in LS-DYNA, for example, and this is used to predict failure. And part of this damage model is that you have a failure criterion. In this case, it's a strain-based criterion modified Moore-Coulomb. And the fracture toughness property is used to describe the reduced incredity due to crack formation. So that controls the softening parameters in this damage model. And the next step is modeling or validation of these simulations doing in the step 1. So we have some excellent input tests performed by voestalpine, and then we have the same kind of tests, or actually the results from the test from Arcelor. First we have bending tests, and then we have run simulation of bending test, but with a notch present, just in order to provoke a crack. So, first of all, as I said, crash situations involve both very large deformation, of course, but also quite high strain rates. So it's quite obvious we need some kind of testing in a range of strain rates, from static to the order of hundreds. So therefore, we have used the high-speed tensor test machine here at LTU. And we have also applied the method developed during the last years. It calls stepwise modeling method. And it's a quite quick method to get the flow stress behavior from initial yielding beyond neck and all the way to failure. So you don't have to extrapolate any data. You get the entire curve, and you also get the failure strain. And this method is based on the use of this digital image correlation. So you can see here some 4 examples. And what you also can see that we're using different kind of geometries of these specimens. And you have a shear, you have a hole in order to have this plane stress, you have a notch to get the very important plane strain condition that Pascal mentioned in the previous presentation. So as an output, besides having the flow stress curve, you also get the triaxiality history from the plastic deformation starts to the final fracture for all different specimen geometries, which is correlated to different triaxialities. And this is, of course, used to calibrate failure model. In this case, it is the modified Moore column. So, and the next one is about how to use to calibrate the software parameters in the Gizmo model. So, in this case, we have run similar experiments as David presented in the first session. It is so-called essential work of fracture test, but in this case, it is at very high strain rates. As once again, we have using our high-speed tensile testing machine, and the specimen geometry is still this double-edged notched. And to the image to the right, you can see how the strain rate develops during the test. So you see, you have a fully plastic stone, which is ligament, which is important for this procedure to work. But as you can see, you have strain rates of order of thousands. So what you're doing in the next step is you run inverse modeling by using LS-DYNA. It's actually LS-Opt to calibrate the softening parameters within the Gizmo model. So I will now leave the word to Ricardo, who will talk about his part. Please, Ricardo.
Thank you, Jorgen. And another important thing about the crashworthiness is the edge cracking situation. It is when the crack starts in the component edges. And to address this problem, we are working with the ductile damage model implemented in Abacus commercial software. This model requires the definition of two parameter sets, the damage initiation and damage evolution. The damage initiation is defined by an equivalent plastic strain, and when this value is reached, the element loses stiffness according to the damage evolution law. The damage is leveled by the damage parameter D that grows from 0 to 1, and when we reach this maximum value, the element is deleted from the mesh. The important thing here is that we calibrate the model using the Dent test, the double-edged notch tension test explained by David in the first session, and we are following the methodology for obtaining the toughness by the essential work of fractures. Next one, please, Jorgen. Through the simulation of this test, we obtain the parameter of the failure model. You can see at the right the damage evolution curve, in this case defined by a bilinear way, and we are using an inverse engineering process like explained Jorgen before, and changing the model parameters to obtain a good fit between the simulation and the real test in terms of the force displacement results. And we do this for different ligament lengths. In our model, we work with shell elements, and the failure model was calibrated for 1 millimeter element length. Until now, this is a full empirical approach, but by our last investigation, we are finding some relation between the damage parameter and the thickness strain. And I will allow find a physical explanation, I hope, for this model, and of course we are working on it. Next one, please. As our colleague Pascal explained in the previous presentation, also we have a methodology to define the maximum strain at failure on bending condition, where we have a strong gradient of strain along the thickness. You know, when we pass from compression to tension in the upper and bottom sheet surface. By the bending test following the standard VDA and with the direct MR correlation, and also using the simulation, we obtain the maximum strain at failure and the traction surface, of course. And we have all this information to apply in the crashworthiness simulations. And now we come back with my colleague Jorgen.
So next step is modeling, and also in that case validation of the simulation we have been performing. And first we have axial impact tests performed by Postalpine, and we have run similar tests at LTU, but in this case we have added 2 high-speed cameras and also put some speckles on the crash boxes. It is in order to measure the deformation during the compression. And we also measure the load versus intrusion, but in this case we could also detect when potential cracks occur and how they propagate. And then we have the bending tests shown by Pascal. LTU has been running the bending test without notch, and Ricardo will show the one with a notched beam. LTU, in our case, we're using Alice Dyna. Once again, we have a Johnson-Cook rate-dependent flow stress model. We have a modified Moore-Column failure model. We have this Gizmo damage model, and element will be eroded when damage of the central integration point reaches unique unity. We have used the full integrated shell elements of size 1 millimeter, and this size is correlated to the size we have with the facets in the DIC for the stepwise modeling method. So we detect the fracture strain with the same size as these shell elements. So these are some example results. As you could see in the table, you have the measured intrusion and the evaluated energy absorption from the experiments in the middle column, and the column to the right, you have the computer results. And as you could see, in more or less all the cases, we have actually underestimated the properties or the crashworthiness of the investigated steels in Crash&Tough. And you can also see an example here for HF 1180 CFB, and you can see there are some underestimated. The calculated, the simulation is the black and the blue one is from the experiments. And another one, this is from LTU. You can see the measured strain to the left, and the video to the right is the corresponding model, and it looks quite similar, but the thing is, unfortunately, you get the correlation when the crash box is too deformed. And this is one image from this crash box test, and maybe you could see some cracks occur, but you can see the motivation or the reason for why we are underestimating the properties, because if you look in these other 2 images from the simulation, you can see we have a crack, but that doesn't occur in reality. So that's the reason for that we underestimate the properties. And you can also see in this comparison between the 3 experimental boxes and the black one is the simulated one. And I think you can see that if you integrate this curve, it will get you a lower value. On the other hand, if we have bending resistance tests without any notch, we are more or less spot on if you compare the measured with the computed. But on the other hand, we don't have any failure here, so you can't say anything. You can't validate the failure mode criteria have been used. What you can say is that maybe we can say something about that the flow stress model that we have obtained is good enough. But once again, we need some kind of failure. So therefore, I will let Ricardo conclude this presentation.
Okay. Also, as you can see in a previous presentation, the crashworthiness of this third generation of advanced steel is excellent. And we never found cracks in the bending crash test using the standard specimen. For this reason, in order to investigate the failure simulation model, we introduced these 2 big notches at the middle bottom part of the specimen. with these two notches, we were able to induce crack and obtain a full material failure in this area. The next one. Here at the right, you can see the comparison between the simulation and the real test. And the simulation is very similar to the real results. Also, remember that the fracture was induced by the introduction of the notches in the specimen. And at the left, we present the force displacement plot. The black line is the real test results, and the red one is the simulation using our failure model, calibrated by the Dent test. Also, you can see that the simulation fit very well with the experimental results. To show the advantages, we did the simulation using a conventional FLC. It is the blue line. I don't show a simulation image because the failure position and the fracture morphology is more or less the same that you can see with our model, but the crash or the intrusion is bigger and the energy is overestimated. The circular point on the plot shows the moment when the crack starts. And you can see that when you are using the FLC, the cracks start too late. Also, we did a simulation with the bending fracture strain, obtaining in the bending condition. It is the yellow line, but this criterion is more convenient to use when we have the positive to negative strain along the thickness in a pure bending condition. And here the failure is under full tension or full traction in the lower part of the specimen. For this, the energy was overestimated with this model. In conclusion, we showed an improvement around the 40% using our model in comparison with the conventional FLC. Of course, the FLC is a good tool, but in this case, it's too conservative in terms of energy absorption. The idea is to apply our energy-based model at the component edges, in all three edges, and combine it with other criterion for the bull material, like the FLC or Gizmo model or every failure surface. And with this combination, the crash simulation will be very good. And this is from our part, and thank you very much for the attention. We can pass to the last presentation.
Yeah.
Thank you, Jorgen, and Ricardo also for an interesting presentation. Also, I wanted to remember, please, if you have answers, if you have questions, please write it in the chat. So we haven't received any question yet, but we hope till the end of the session we can have some. Now we can move to the final presentation of this workshop, which will be performed by Daniele De Caro. Daniele is a material specialist. He works in the metals department at the Fiat Research Center, and he will talk about the implementation of this new third generation steel grades in automotive components.
Thank you, David. Thank you for the introduction. I'm going to share my screen. Okay, so I hope you see it. Okay, perfect. So thanks for the introduction. In this last section, I will give to you an overview about the third steel generation application in real automotive parts and the contribution of the Fiat Research Center to this project. So we are going to see a brief introduction about which are the main automotive challenges today, so why we need the innovative material, a current scenario about third steel generation, then we will go straight into the results of the project, and at the end we will have a short insight about the future scenario and the main achievement of the project. So, first of all, as everyone know, automotive industry is facing a lot and is going to face a lot of challenges for the future. So we need in the future to develop a better energy efficiency vehicle. That energy efficiency can means for internal combustion engine car to consume less fuel, and for electrical vehicle to consume less energy. We have to increase the safety of our car, so increasing the strength of our component during the crash event. We have to produce a sustainable vehicle because we have only one planet and we have to preserve it. So we have to do the car in a sustainable way. And last but not least, we have to produce a vehicle at affordable cost for our customers. So we have to reduce the cost of our car, especially for electrical vehicles. So how we can answer to this question? We can produce a vehicle with using cleaner fuel, especially for some segment like EV truck or light duty vehicle. We can produce electrical car like we are doing for passenger cars, so reducing the emission, the CO2 emission in the usage of the vehicle. But especially we need more and more introduction of advanced materials like third generation. Why? Because lightweighting in the future will play a role more and more important, both for the current internal combustion engine vehicle and electrical car. For internal combustion engine vehicle, is quite known that there are very tough regulation that will increase more and more in the future. So in the past and up to the production of the last internal combustion engine vehicle, one of the way to reduce the CO2 emission is to reduce the weight of the vehicle. Consider that for 1 kilo that you can save on your car, you can reduce by 0.08 grams of CO2 per kilometer the emission of your vehicle. But weight reduction will play also a really big role for the future electrical vehicle. The current scenario say to us that currently on the market, the electrical vehicle has a weight higher than the brother internal combustion engine car due to the battery pack. So because you have to assure that the customer can drive for enough kilometer the vehicle, and the increase of weight range from 200 to 500 kilo per car. Adding the weight, the necessary weight due to the battery pack, this is a problem because increasing the weight of your vehicle increase the mass, and this means more inertia. So it means that for you need something more to achieve the same safety target that you had for internal combustion engine, and moreover, you need to protect your battery pack. So one of the options is to reduce the weight of the vehicle and increase the strength of your component. And last but not least, the second behavior that is affected by weight is the range you can drive your car. So it's clear that if you add mass to your car, you have to use more energy and you will drive less kilometers. So one of the way is to reduce the weight of your vehicle to drive more. So currently, one of the most appealing material on the market is the third steel generation. That has been well described by my colleagues before. The reason why is that they have a high strength, so like and more than first steel generation, but has also higher formability, than lower steel grade of first steel generation. So this means that you can reduce the thickness of your component, maintaining the same overall strength of the part. reducing weight and reducing also the usage of the material in the vehicle. It is also important for sustainability. These properties, as described before, are achieved by a perfect mix of different steel phase microstructure like Finite, martensite, ferrite, retained austenite. And there are already some winning application on the market, like in the Alfa Romeo Giulia Stelvio, where Trip Binitic 1000 has been applied for the first time in the underseat beam. This is one slide presented by Eurocar Body Engineering, and the meaning is that we already apply it and we are able to save weight in the vehicle. But this is not enough, because still the volume of third generation in the vehicle across the world is too low. For this reason, in my opinion, this project was very important to increase our knowledge about third generation. So going straight to the activities about the implementation of these materials in a real industrial component, together with the partner we choose the two different parts. Because we had different material thickness availability for the project for the different grades. So for the dual phase high formability 1180 from Western Pin, we selected a side seal reinforcement, currently made in dual phase 800 megapascal grade. And for the other grades, so the version of 40 and the two dual phase 1000, we choose a battery pack reinforcement made also in dual phase 800. The goal of this work package was to understand if with these new materials, so increasing the strength of the material we are using, the component is feasible, so assess the formability in real parts, and so understand which can be the lightweight potential for future application in the new vehicles. Going to the results, before to run experimental stamping test, we performed feasibility study in a simulation environment for forming simulation for both of the components. This forming simulation has been done on the highest strength material grade, so the 1180 high formable grade. And on side seal, we can see that the simulation say to us that the component is feasible. There is no any risk of cracks in any area. And the good news is that the results of the simulation match very well with the experimental results. We stamped several components using the same material, and there are no cracks. Obviously, there are some defects in some area where some wrinkling defect appears, but this is normal because we were using a different material and different thickness in respect to the current production. So the dies was not set up for that configuration. Otherwise, looking to the battery pack reinforcement, the forming simulation for both of the components showed to us that in some area, some critical area, some cracks can occur at the end of the stamping test. Nevertheless, the experimental results show something different. So in every component we were able to stamp. No any cracks were revealed, so the component was okay and feasible with the highest stick grade 1180. And obviously also in this case there are some defects. And so these tell us that the standard method we use to characterize the material and to perform simulation, also in forming, is too conservative, and so we need something more to better explore the failure mode of these materials, like well explained by my partners in the previous section. And here I can show also that otherwise on dual phase 1000, so the first steel generation, the formability is effectively lower than 1180 high formable grades, and some cracks on some component occur due to the two critical area due to high strain. Moreover, on all the materials we performed high tensile, high strain rate tensile test using the Hopkins bar based on our laboratory in Turin at CRF. These are quite common tests that we perform to assess the crashworthiness behavior of the material at sample level. And this data has been used by input by our partners for high strain rate simulation. The results show that the ultimate tensile strength of the material generally slightly increasing the strain rate means that the material can sustain more energy during a crash event. That is a good news. So about the future scenario, from our research, I can say that the world is going in this direction. So in our opinion, the volume of third steel generation in the future vehicle will increase from today 5% up to 12%, up to 20%, because as I said before, lightweighting is going to be more and more important. I see three potential opportunity for the spread of this steel. One is to substitute, as we have seen in the project, the first steel generation, reducing the weight also of the component. Replace press-hardened steel when press-hardening is not necessary. I mean, press-hardening has a high initial capital cost. Sometimes we use it, every car maker use it also when it's not strictly necessary. So this means also cost reduction. And there can be new application on electrical vehicle, especially on new components like the battery tray, where currently is dominated by aluminum. But we are seeing that some new concepts in steel are arising, and there are a lot of projects to study new concept on steel. For sure, third steel generation can play a big role. So going to the conclusion, the main achievements of this project, in my opinion, was that we were able to have a fruitful and useful collaboration with a lot of strategic partners, exploring the full potential of third steel generation and their failure behavior in different conditions. We were able to assess the formability and so the potential application of this steel in real components, substituting dual phase 800 mainly. And we were able to increase our knowledge about the failure behavior of this steel. There are still a lot of challenges. So for sure, we have to, first of all, we have to open our mind inside car maker, so inside the automotive industry, in order to use and replace the standard material model that we use to model the failure of the steel, using the new one that are arising like in this project in Crash&Tough, because only in this way we can be able to catch the real behavior of the material and unlock a new lightweight potential for the new vehicles. Then in my opinion, we have to go further with welding evaluation of third steel generation. We know that there can be some problems, so we need to work all together, all the stakeholders together, in order to understand better this behavior. And the last but not least, we have to use a new approach to control and predict the spring-back behavior of third steel generation. Because sometimes the model is not able to predict this behavior, and especially going up to 1180 and 1300 megapascal grades, it becomes a critical behavior. So thank you very much for your attention, and see you on the next project.
Thank you very much, Daniele, for your interesting presentation, and also for raising this future challenge for future projects. So hopefully we can continue working on this direction. Well, I haven't seen any questions in the chat now. If you have, well, we have some extra time now. We want to think. We have any doubts to the content we have shown during the event. In the meantime, I have a couple of questions that I wrote during the presentations. The first one is maybe to Jorgen, also, which you show the evaluation, or you characterize the influence of strain rates and on the flow curves and so on. Did you notice some very relevant effect of the strain rate on these flow curves and fracture strains for the different investigated steel grades?
I'm trying to share my presentation here. Maybe it's easy to address the question. Is it that one? Sharing is paused. Do you think I could share my?
Are you sharing?
I'm trying. Let's see if I.
Yeah, now we can see.
It's easier to. So I go from. So is this the one?
Mm-hmm.
Is this the one, David?
Yeah.
So, could you please quickly repeat the question?
I was asking if you have noticed a relevant effect of the strain rate on these flow curves and the fracture strains obtained for the steel grades.
You could
at least
see
in the range that you investigate.
Yeah, you could see this is an example. Okay, yes, you have some hardening because of the strain rate, but it's not very hard. And when it comes to the failure strains, we concluded that we couldn't see any dependency of the strain rate when it comes to a failure strain for a certain specimen geometry.
Well, of course, at least in the range of strain rates.
Yes, at least in our range, yes, from 1 to 100, 110 and 100. So. Also,
one other related question, maybe I think Pascal can help us here, because I know in the project we haven't looked at it, so I guess the answer is no, but have you evaluated somehow, maybe in other projects, because you mentioned the fracture strain in plane strain is one of the most important, we're talking about this failure behavior during crash. Have you evaluated this influence of strain rate in this fracture strain and plane strain?
Yes, we showed in the presentation, we had the result for the different grades, yes. Maybe I did not understand well your question.
No, I was asking if you have evaluated the influence of a strain rate also in these fracture strain values.
On the strain rate. Sorry.
Yeah. Not in the project. I know not in the project, but maybe in previous research or in other.
Yes, we did it by our own during, but it was not possible to do that on V-bending tests. But we did the evaluation on some notched samples that we were able to tensile with our dedicated tools for dynamic testing. For example, high-speed hydraulic machine. We were able to reach some 10 strain rates about at least 100 per second, and we generally observed an increase of the ductility with the strain rate. So if we make some characterization in quasi-static condition, we can provide some conservative criteria regarding the fracture strain.
Okay. Thank you. I think, well, more or less, so Jorgen, you can correct me if I'm wrong, but I think we observe also something similar regarding fracture toughness, no? This essential work of fracture at different strain rates. Observe also similar behavior. In general, the ductility tends to increase with the strain rate.
But I think that when it comes to this failure criteria, I think it could be wise to combine this V-banding test with this kind of test we have been doing. But of course, the V-banding test gives the most important point because it's the lowest value. So in some way or another, these two should be combined. That could be an improvement.
Okay, now to finishing, I have one, I think, more general questions, so mainly to the steel makers, also from the more industry partners like CRF. So how the results or the outcome of the project do you think have contributed? On the one hand, to future steel development? No, this is a question for the steel makers, maybe Johannes or something from someone from Marshall.
Well, we learned again that regarding toughness, it is necessary to have a microstructure with low hardness contrast. You should have a quite homogeneous microstructure. I think this is one of the most important things we learned from the project.
On the other side, in the more industrial side, I think more or less, Daniela, you already mentioned in the presentation.
Yeah.
How do you think that these results have contributed?
These results are this project was very important for us because now we have more knowledge on that. We have a relationship with the whole of you, so we can work together to try to implement this model at industrial level. It won't be easy because we know that any change is hard, but for sure is fundamental because sometimes we are not able to accurately predict the crack in stamping or in crash, and this model I think that has a better forecast in respect to the standard one. So I think that we have to go further with other projects and try to make it industrially feasible.
Thank you for your answers, and also thank you all the participants, all the speakers for your participation, of course, and thank you for making this workshop and the project also possible. Now, before concluding this event, I wanted to remind or to show maybe Marina also put some information about other events which are also related to the topic of this workshop. Also to the two projects also related, which is the Form Planet and the Tough Steel, as I introduced previously in my presentation. The next event is the 2nd of February. We have this final conference of the Form Planet project, which is related to the sheet metal formability, and we will present advanced characterization and modeling techniques for the sheet metal forming industry. Also, you can find more information and registration for free here in this link. And also an open day for the presentation to the society, this Tough Steel project, which is the Tough Steel Open Day. And also the same, you can find here in these links more information and also the link for registration. Now, well, thank you again, all the participants, of course, also Marina, who is also behind the cameras, also helping us with the organization of this webinar. I hope you enjoyed the presentations. And well, let's see you in the next event. Have a nice afternoon. Bye.
Have a nice afternoon. Thank you very much. Goodbye.
Thanks to everyone. Bye-bye.
Bye-bye.